Someone might argue, if it's expanding, it must be getting bigger, right? The thing is, it's not that matter is expanding into some larger space. It's that space itself is creating new space. So, over the next few dozen minutes, we're going to trace this concept all the way through. From Hubble's redshift, to the microwave background noise on an old TV screen. From an early universe the size of a beach ball, to Einstein's so-called blunder, the cosmological constant. And in the end, you might just find that what we call the outside is perhaps nothing more than an illusion we can never reach. To make the abstract concept of cosmic expansion easier to grasp, let's start with a simple analogy. Imagine you're in your living room blowing up a balloon. Air goes in, the rubber stretches, and the balloon takes up more room. The reason it can get bigger is because there's still space around it to grow into. Your living room is its outside. And because of that, it's natural for us to think of cosmic expansion in the same way. As if space is pushing out into some larger universal room. If it's getting bigger, it should have a boundary. And it should have an end. That idea seems reasonable, but it actually falls right into a cognitive trap. Physics tells us the universe doesn't work that way. When space expands, it isn't pushing into anything external. Because there is no such thing as an outside. No container, no empty void waiting to be filled. The universe isn't just getting larger, it's creating its own space as it goes. A more accurate analogy would be this. If you wanted to draw a circle larger than the paper you're using, you wouldn't go find a bigger sheet of paper. Instead, you'd make the paper itself grow to accommodate the line. This sounds strange, because in our everyday experience, everything that grows has to grow into somewhere. Plants grow into the air. Cities expand into the countryside, and ice spreads across the water. So, we subconsciously use inside and outside to make sense of the world. But what if you are the paper itself? It's just another diagram again. The very concept of an outside loses its meaning. So, the question is no longer where is the universe heading? But rather, how do we know that space itself is growing? The answer comes from the light of the furthest stars. Scientists only realized this counterintuitive fact by observing distant galaxies. Edwin Hubble discovered that the further a galaxy is from us, the faster it's moving away. At first glance, this seems to imply that we are at the center of a cosmic explosion. As if everything is flying outward from this exact spot. But the truly bizarre part is, galaxies aren't moving through space to escape. It's the space between them that is being stretched. A reversed balloon analogy makes this even more intuitive. Think of galaxies as dots on the surface of a balloon. As the balloon grows, the distance between the dots increases. These dots aren't crawling across the surface. The surface itself is expanding. Every dot sees the others moving away. And yet, no single dot is the center. Replace this two-dimensional surface with the three-dimensional space we inhabit. And you arrive at the key conclusion. The universe isn't expanding into some external space. Because there is no outside for it to enter. It is growing while simultaneously creating its own stage. This conclusion is not only a headache for the audience. It also left the geniuses of that era scratching their heads. Even Einstein was initially reluctant to accept it. But the thing is, this seemingly impossible expansion is happening right now at a speed you can hardly imagine. Next, we have to answer a tough question. How can we be sure this isn't just a clever metaphor? The clue is hidden in the journey of how light gets stretched. When a distant galaxy sends us light, the wavelength is fixed. It has its own unique fingerprint. But as this beam of light travels through ever-expanding space, the path beneath it gets stretched longer and longer. Imagine you are walking on a moving walkway that slowly extends. Your stride stays the same, but the path beneath you is being quietly stretched out. By the time you reach the end, the actual distance covered far exceeds your number of steps. For light, the result isn't about traveling further, but about its wavelength being stretched out. So, by the time blue light from far away reaches us, it has turned into red light. The key point here is, this isn't the Doppler effect where a frequency changes due to speed, like when an ambulance zooms past. It's that space itself has been stretched during the journey, widening the gap between every crest and trough of the wave. This is what we call cosmological redshift. It serves as direct proof that the expansion of space is independent of the movement of objects within it. To put it more intuitively, a mechanism capable of stretching the ruler you use in your three-dimensional world is pulling the wavelength of ancient starlight into a whole new range. And here is an order of magnitude that will blow your mind. The light from the most distant observable galaxies has had its wavelength stretched to nearly 40 times its original length. Intense ultraviolet light has been dragged all the way into the faint infrared spectrum. This means that throughout its journey spanning billions of years, the overall scale of the universe has also expanded by nearly 40 times. Consequently, the galaxy you see through a telescope appears small and dim. But when the light first left that galaxy, the universe was much smaller than it is today, and it was much closer to where our Milky Way would eventually be. Clearly, space isn't just getting a little bit bigger. It is undergoing a continuous and grand-scale stretching. More importantly, this stretching isn't happening in some remote corner. It is happening everywhere. Right at this moment, the space inside this room is also trying to grow larger. The reason you can't feel it is because the electromagnetic forces between atoms hold matter firmly together. At this scale, the force of expansion doesn't stand a chance. It is only between galaxies, in places where this atomic glue is missing, that this expansion can truly take hold, carrying them further and further apart. It's just like raisins being spread apart as the dough rises. The raisins aren't actively swimming through the dough. It is the dough itself that is growing. So, when you ask what the universe is expanding into, it's just like asking where is the dough going. Don't forget, you yourself are a part of that dough. But since space is stretching everywhere, just how far can we actually see? To put it bluntly, we are living inside an invisible cosmic prison. Its walls were built by time itself. When you look up at the starry sky at night, you might think the entire universe is laid out right before your eyes. But the truth will completely shatter that perception. What you can see is likely less than 4% of the actual universe. The reason is quite simple, and yet quite cruel. The speed of light is limited, and the age of the universe is limited. The farther out you look, the further back you are traveling in time. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at Alpha Centauri, you are seeing it as it was 4 years ago. When you look at the Andromeda Galaxy, you are seeing it as it was 2,500,000 years ago. The age of the universe is about 13,800,000,000 years. This means that even the oldest light has only traveled for, at most, 13,800,000,000 years. To finally reach you, galaxies beyond this travel time are effectively non-existent from your perspective because their light is still on its way. But don't forget, during all this time, space has been constantly expanding. When those distant galaxies emitted the light we are receiving today, they were much closer to us. By the time this ancient light finally arrived, expansion had already carried them 46 billion light-years away. So, our observable universe is just a bubble with a radius of about 46 billion light-years. Outside this bubble, there are countless more galaxies and stars. Perhaps there is even another version of you reading these very words. You can't see them, not because they aren't there, but because their light hasn't had time to reach you. So, everything beyond the bubble falls into the unobservable universe. It's not a wall or a barrier blocking you. It's the laws of physics setting a limit. You can think of it like a thick fog that limits your view in every direction to a certain distance. You know there is a world beyond the fog, but you simply cannot reach it. Furthermore, if the universe is infinite in scale, then the fraction of the whole that your tiny observable bubble occupies is essentially zero. It could almost be written as a perfect zero. To understand exactly where this wall of time lies, we must look back at one of the oldest rays of light. Today, the oldest light in the universe is rushing toward you at 600 million miles per hour. It predates the birth of our solar system. It predates the formation of the Milky Way. Its journey began when the universe was only 380,000 years old. Back then, the universe was a sea of scorching plasma. It was so hot that not even atoms could form. Any photon couldn't travel more than a few inches before being snatched up by charged particles. Only when the universe continued to expand and cooled to a low enough temperature did protons and electrons finally combine to form hydrogen atoms for the first time. Only then did the dense fog clear. The universe suddenly became transparent. Light could travel freely. This is the recombination era. Those very first photons that escaped are what we observe today as the cosmic microwave background radiation. It is everywhere. It fills every single cubic inch of space. Even that little bit of static noise you'd see when changing channels on an old-fashioned television set is about 1% comprised of this primordial light. More importantly, it marks the edge of everything we can see. You can never look past this layer. The horizon, because the earlier universe was like an opaque, sun-like fog. Whatever happened before 380,000 years ago will always, to put it bluntly, The cosmic microwave background is that first brick wall. It defines the limit of our observation. On the surface, this wall seems to be receding. With every passing second, light that has traveled for 13.8 billion years plus one more second reaches us. Therefore, the radius of the observable universe increases by 1 light second every second. That is roughly 300,000 kilometers of new space entering our view. By the day, we get to see about 16 billion miles more of the universe. But once you think about it, another layer comes to mind, although the screen is getting bigger. The sources of that light are being carried away by expansion. For example, a galaxy that emitted photons 13 billion years ago has very likely been dragged 30 billion light-years away by now. What we see is how it looked back then, not where it is today. This sense of dislocation, like the screen is expanding while the actors are retreating. Just the everyday routine of cosmological observation. And so it goes. Back then, the universe was smooth to near perfection. The temperature fluctuations were only a few parts per million. Yet it was these tiny ripples that ultimately gave birth to the galaxies of today, and to us. Now, let's cast our gaze toward what might lie beyond the bubble. Based on our measurements of the cosmic microwave background, the universe is approximately uniform on the largest scales. This means that no matter where you set your starting point, the composition and proportions remain much the same. It's like a bowl of cake batter mixed so thoroughly that every spoonful contains the exact same ingredients. Extending this line of reasoning, if our observable universe contains roughly 2 trillion galaxies, then in another region of equal size beyond the horizon, there is a high probability that it also contains about 2 trillion galaxies. And in the regions beyond that, it remains the same. This pattern would just stretch on, patch after patch. What's even more mind-bending is this. If space is near infinite in scale and maintains this uniformity, then every possible arrangement of matter within any given volume must eventually repeat somewhere. It sounds like metaphysics, but the conclusion is purely mathematical. A finite number of microscopic arrangements combined with an infinite volume makes repetition an absolute certainty. At this point, the metaphor from the previous section about the paper and the drawing becoming one aligns perfectly with the observational evidence here. We don't need to look for an outside to contain the universe. What we really need to track is how this paper is being continuously stretched, and how, as its scale approaches infinity, it fills itself with every possible outcome. Since this paper can potentially contain every possibility on an infinite scale, the most jarring conclusion follows. Repetition is unavoidable. So, let's use a deck of cards as a baseline. If you could shuffle the deck an infinite number of times, an identical sequence of cards would eventually appear again. The universe works in much the same way, except the cards are replaced by atoms and their arrangements. Consequently, in a place incredibly far away, there must exist another version of you who is reading this very text. This is not a metaphor, but a literal deduction. Because in those regions where light will never reach us, quantum mechanics has already arranged matter in every possible configuration, and that includes one that matches your exact state at this very moment. So, there is a version of you who stops reading right now. There is a version of you who was never born. And there is another version of you living in a version of Earth with a completely different history. Mathematics even provides a sense of scale. These copies exist about 1 followed by 115 zeros meters away. This number is so massive that if you were to write it out in full, the length of the number string alone would exceed the size of the entire observable universe. Yet, as long as space is truly infinite, such a distance is still considered finite. And so, somewhere out there, another you just realized this very fact. And a bit further away, there is yet another you realizing that the previous you just realized this fact. However, all of this rests on one premise, that beyond the horizon and here on our side, things are more or less the same. But what if it isn't similar at all? Recent observations suggest that the patch of the universe we inhabit might be a bit thin. Like a cosmic void where the density of galaxies is lower than the average. If that is truly the case, then crossing the observable boundary might reveal much more crowded space, more galaxies, more black holes, and far more violent activity. Or it could be the complete opposite, a deep space that is almost entirely empty. Bolder theories even push our gaze back to that very first moment. A brief but incredibly intense period of cosmic inflation might have torn the whole thing into many pocket universes with vastly different properties. They might possess different physical constants, different particle spectra, or even follow entirely alien laws of physics, making our textbooks useless the moment you step outside our borders. And the reason everything seems so normal here to us is simply because we happen to live within the specific recipe of this pocket. But there is an even deeper thorn that needs to be addressed head-on. What if the universe isn't infinite at all? An infinite universe that expands brings us to a seemingly elegant paradox. How can you make infinity any bigger? The answer mathematics gives is, you can't. Infinity plus any finite number is still infinity. Multiplied by 2, it is still infinity. You cannot add anything more to something that already contains everything. Yet, observations clearly tell us that space is stretching everywhere. To resolve this hook, the key is to discard the intuition that equates expansion with becoming more infinite. A more accurate way to put it is, the scale factor is simply getting larger. Imagine an infinite sheet of graph paper with each square being 1 inch wide. Now, imagine stretching the whole thing so each square becomes 2 inches wide. The paper remains infinite, the squares are still countless. But the distance between any 2 points has doubled. That is the very essence of how the universe expands. It isn't about adding another layer of infinity to what's already there. It's about stretching the very fabric of space itself, making every distance grow proportionally. So, a galaxy that is 100 million light-years away today, back when the universe was only half its current size, was only 50 million light-years away. And then, the logic follows. If the universe is infinite right now, then at the moment of the Big Bang, it must have been infinite as well. The Big Bang is no longer like fireworks, exploding matter out from a single point. Instead, it's more like infinite space starting to expand everywhere all at once. And filling up with energy. In other words, the Big Bang happened everywhere throughout infinite space. It has no center, no boundary, and no outside. Any location can claim to be the center. Because no matter where you look, the view of the expansion looks exactly the same. This perspective explains why, in every direction we look, we see almost the same universe, and why we can't find an edge or a center. On the other hand, it also raises a new question. If the universe contains infinite matter and energy, why don't we end up with infinite density? The answer lies in the definition. Density is simply the total amount divided by the volume. Even if both the numerator and the denominator tend toward infinity, as long as they grow at the same rate, the ratio can still be a finite number. And so, the universe can hold infinite matter within infinite space, while maintaining a finite average density, roughly a few hydrogen atoms per cubic meter. From here, the theory starts to get personal. In a truly infinite universe, any event that obeys the laws of physics will happen an infinite number of times. It's not just another you that repeats, but every single version of every story. Tragedies and triumphs, beauty and cruelty, they're all playing out somewhere. If that feels a bit unsettling, we could turn our focus back to the possibility of a finite universe. A universe with an end forces us to face even thornier questions. What lies beyond the boundary? Can space truly have an end? If you were to try and cross that boundary, what would happen? These questions lead many scientists to prefer a model where space is massive, or essentially infinite. Although it's hard to wrap your head around conceptually, it at least tucks away that question of what's outside the boundary. When we look at the latest measurements of the cosmic microwave background, we are either facing an infinite universe, or one so vast that it appears perfectly flat, with no measurable curvature at all. The simplest explanation is that space just keeps stretching forever in every direction. So, the expansion we see today isn't like adding new rooms to a house. It's more like stretching out an infinitely large piece of fabric that was already there. But what exactly is the mechanics driving this constant stretching? To put it bluntly, the universe is churning out new space from the near-nothingness of the quantum vacuum, at a rate that would make every factory on Earth green with envy. Doing some rough math, every single second, the volume of the observable universe increases by about 1 followed by 78 zeros in cubic meters. This number is so massive that even if you counted 1 every second, it would take you far longer than the current age of the universe. And if you were to multiply that time by itself billions of times, it still wouldn't be enough. But the quantum vacuum isn't really nothing. It's more like a pot of boiling, never-ending foam. Virtual particles constantly pop into existence and vanish in a tiny fraction of a second. This is what we call quantum fluctuations. It means every single point in space carries its own energy. What really defies intuition is that this vacuum energy expresses itself through gravity. Unlike the gravity of matter, which pulls things together, vacuum energy creates repulsion. It pushes space outward. The more space there is, the more vacuum energy there is. The more vacuum energy, the faster the expansion. And the faster it expands, the more new space is created. Crank this circuit up to the max, and you trigger a runaway burst of inflation. In the very first, fleeting instant, this process went into overdrive. Space was expanding faster than light could travel across it. Now, that doesn't mean anything was moving faster than light. It's just that the treadmill was accelerating. Light on that treadmill just couldn't keep up with the treadmill itself. During that time, a region smaller than a proton could be stretched to nearly the size of a basketball in an unimaginably short interval. It sounds like science fiction, but the laws of quantum mechanics demand it happen. As long as you pay it back within a short enough window, you can borrow energy straight out of the vacuum. During the inflationary phase, the universe borrowed a massive amount of energy from the vacuum to set up a factory for churning out space. Then, it used the expansion itself to settle the debt. It's like taking out a loan for a printing press, then using the money you printed to pay off the loan. The problem is, this mechanism worked a little too well. It was only supposed to create enough space to solve a few cosmological puzzles. But it didn't stop when it was done. Instead, it went into overtime, producing way more territory than was ever needed. And so, our entire observable universe is nothing more than a tiny patch on this gargantuan inflationary tapestry. Imagine blowing up a balloon to the size of the Earth, while everything we can currently see is just a point the size of a pinprick. What's even more intriguing is that, although that early inflation has long since ceased, the expansion is still going on today. It's just that the rhythm has shifted to a different tune. Dark energy makes up about 68% of the total universe. It behaves almost exactly like vacuum energy, filling space uniformly and providing a repulsive kind of gravity, driving the expansion to accelerate. As volume increases, new dark energy keeps appearing to fill that new space. It sounds like it's creating energy out of thin air, which seems to clash with the law of conservation of energy. The key to resolving this lies in the gravity ledger. Gravitational potential energy is negative. As space stretches out, the gravitational binding energy between matter decreases. That extra negative energy perfectly offsets the positive energy of the new dark energy. The result is, the universe just keeps generating new space, while keeping the grand balance right around zero. According to this script, inflation will continue for an incredibly long time, far beyond the scale of human imagination. At every single moment, new space is born, new dark energy emerges, the stretching of the universe continues to accelerate. The reason the universe grows isn't to occupy some place on the outside, but because the expansion itself is creating its own stage. Where should we go to look for it? The clue isn't in some distant myth, but hidden in a very humble place. When you switch an old-fashioned television back and forth between channels, within that static noise, about a small fraction, actually comes from the earliest light of the universe. The answer is right there in that static. In 1964, at Bell Labs, Penzias and Wilson just wanted to get rid of that annoying hissing sound in their antenna. So they changed directions, calibrated the equipment, and even cleaned the bird droppings off the antenna. But the noise wouldn't go away. It turned out that it wasn't a malfunction, but the echo of creation. They had stumbled upon the cosmic microwave background radiation, which is the afterglow of the Big Bang. Because space keeps expanding, this ancient light has been stretched and cooled along the way. Today it is only about 2.7 Kelvin above absolute zero. Precisely because of this discovery not only won the two of them a Nobel Prize, but also provided the most direct evidence that the universe is expanding. More importantly, this background light doesn't just exist. It also carries the fingerprints of expansion etched into its spectrum. Initially visible light at about 3000 degrees Celsius. As space was stretched, it first slid into infrared, then dropped into microwave, and finally extended into radio waves. At the same time, the brightness of the entire sky is almost as flat as a mirror, uniform to within just a few parts per 100,000 in fluctuations. This perfectly matches the predictions of inflation theory. If there hadn't been an incredibly rapid expansion early on to smooth out the irregularities, we would be seeing massive temperature differences right now. But that is not the case at all. So the question takes a step further. Where did those tiny, remaining fluctuations come from? The answer lies at the quantum level. Inflation stretched quantum fluctuations from subatomic scales to cosmic proportions. These faint energy ripples later became the seeds for galaxies and stars. In other words, the reason you are able to read this right here is because the universe itself magnified quantum uncertainty into the macroscopic world. Next, the evidence was mapped out. Through the Cosmic Background Explorer and the Planck satellite, humanity has rendered this map of temperature fluctuations in incredible detail. And when the results were checked, the distribution of angular scales matched the theoretical curve of inflation almost point for point. Based on this ancient microwave light, we can not only see but also measure the universe. In terms of geometry, space is nearly flat within our measurement precision. In terms of composition, ordinary matter makes up only about 5% of the total. In terms of dynamics, the expansion rate and the age of the universe can both be narrowed down to a very precise range. More intuitively, the data also gave us a staggering sense of scale. The entire observable universe today was once compressed into a volume about the size of a beach ball. This compression isn't about stuffing things into a box, but about space itself being squeezed tight. That beach ball was not a container holding the early universe. It was the universe itself at that time. There was no outside, and there was no surroundings. There was only that clump of compressed space-time. It then began to expand and cool. And that is how we got the starry sky we have today. So, where did the energy that pushed this space-time apart come from? To find the answer, scientists shifted their gaze to a more stable celestial phenomenon. In 1998, two teams used Type 1a supernovae as standard candles, hoping to measure how the expansion should be slowing down under the influence of gravity. The approach was simple, by comparing the actual brightness of these supernovae to their standard brightness, and factoring in the redshift, they could calculate exactly how far away they were. But once they plotted the data, the conclusion was completely flipped. The distant supernovae were dimmer than expected, meaning they were farther away than the standard model had predicted. In other words, the light has had to travel across even more space than we first imagined. So, not only has the universe not hit the brakes, it's actually speeding up. This discovery also earned a Nobel Prize. And at the same time, it introduced us to a new player. This player is dark energy. It currently accounts for about 68% of the total mass energy of the universe. Far more than all ordinary matter combined. And it has much more sway over the big picture than dark matter does. The weird thing about it is that it neither clumps together nor dilutes. Matter gets thinner as volume increases, but the density of dark energy remains essentially constant as the universe expands. As a result, the larger the universe grows, the stronger its total influence becomes. Early on, matter and radiation called the shots, while dark energy was just in the background. But as matter was pulled further and further apart, the repulsive effect of dark energy started to rise. About 5 billion years ago, it took the lead. Ever since then, the universe has been in an era of acceleration. If we follow this trend forward, more and more distant galaxies will start moving away from us, at a rate faster than light can keep up with. Eventually, they will slip out of our observable range forever. But what exactly is this invisible pusher? The leading candidate is vacuum energy, which is the ground state fluctuation of quantum fields in what looks like empty space. According to a simple calculation from quantum field theory, the vacuum should be packed with massive amounts of energy. Yet when you compare that to observations, there is a discrepancy of 10 to the power of 120. This is arguably the worst prediction in the history of physics. So, either we are missing a key piece of the puzzle regarding the quantum world. There is some mechanism in nature that cancels out almost all of that vacuum energy, leaving behind just that tiny bit needed to drive the acceleration. Beyond that, some have suggested that dark energy might be a new field permeating the universe. And others have even proposed rewriting the laws of gravity on a cosmic scale. No matter which path we take, the current situation points to one conclusion: we are in much the same position as ancient humans gazing up at thunder and lightning. Yet, it is indeed continuing to shape the destiny of the universe. Speaking of the universe's destiny, we need to pull the camera back to an even earlier moment. Many people ask, what happens if the rate of expansion is faster than the speed of light? The answer doesn't actually violate the principle that nothing can travel faster than light. Because what's moving so fast isn't an object. It's the very scale of space itself. In the fleeting instant right after the Big Bang, the universe entered what we call the inflationary period, where the distance between any 2 points doubled and doubled again in an unimaginably short span of time, so fast that even light couldn't keep up. To visualize it, imagine 2 ants standing on a balloon that's being rapidly inflated. No matter how fast they crawl, they'll only drift further and further apart. In terms of orders of magnitude, inflation expanded the scale of the universe by at least a 1 followed by 26 zeros. And all of this happened in roughly 1 divided by 100 sextillionth of a second. For comparison, light only travels 30 centimeters in a single nanosecond. Driving this frantic stretching was a quantum field called the inflating field. Unlike many fields where the ground state energy is zero, it was trapped in a high-energy false vacuum, much like a pool of water suspended high above the ground, able to continuously pump energy into space in an instant. The terrifying thing about exponential growth is that it seems subtle and hidden in the beginning, but takes off in a sudden, violent sprint at the end. It not only smoothed out the early fluctuations, making the sky look almost uniform, but also stretched the curvature of the universe until it was nearly flat. It even amplified tiny quantum fluctuations into the seeds of all future structures. Your galaxy, your stars, and even the atoms within your body can all be traced back to the random ripples of that single moment. But immediately after, a more unsettling question arose. If inflation really happened back then, why would it only happen once? The kind of quantum field that drove the initial inflation is highly likely to still be lurking behind the scenes today. Whenever conditions are right, it could trigger a new round of exponential stretching. It could start at any time, in any place. And a new inflationary bubble would form right there, expanding outward at nearly the speed of light. Everything in its path would be rewritten. Inside that bubble, a completely new set of physical laws would take hold. Our atoms would be torn apart. The laws we know would instantly cease to function. And the most terrifying part is, we wouldn't get any warning at all. But for the theory of cosmic inflation, this isn't even the most mind-blowing implication. What's more likely is this. Our universe is just one tiny bubble in an infinite sea of bubbles. At this very moment, as you're reading these words, countless other universes are being born somewhere else. Each carries its own distinct natural constants and families of particles, perhaps even its own physics grammar. It sounds like science fiction, but it's actually a logical extension of inflation theory. If it could happen once, then quantum fluctuations would make it repeat endlessly on a grander scale. And so, bubble after bubble gets blown into existence. Each one expands, then cools down, and might even go on to sprout its own galaxies and planets. Our universe is just one of them. In other bubbles, gravity might be so intense that stars collapse into black holes the moment they ignite. Or, gravity might be so weak that matter could never come together at all. Some bubbles might lack electromagnetic forces, making chemical reactions completely impossible. Others might stay in a state of eternal inflation, never cooling down enough to even form atoms. The vast majority of these bubbles are likely far too barren to host life. But in a sea of bubbles that is truly infinite, even the most unlikely combinations will eventually appear in some corner of the void. And that's why the anthropic principle takes on a new meaning. We don't live in a universe that appears fine-tuned for us, because it was custom-made for our existence. It's simply that only this kind of universe could foster observers like us. In other words, we see it only because it allows us to exist. From here on out, the questions aren't just about physics. They delve into philosophy. If there really are an infinite number of universes, then every possible experience must be playing out somewhere. The choices you didn't make are being played out by you in another bubble. The tragedies you managed to avoid have befallen another version of yourself. And your unfulfilled dreams? They're blossoming in another branch of reality. In this light, the concept of being unique is diluted until it almost loses all meaning. The weight of those choices gets spread thin across countless parallel timelines. The stickier part is testability. By definition, all the other bubbles are beyond our horizon. They don't send us any light, nor do they leave any gravitational footprints. We can neither prove their existence directly, nor can we measure their properties. Precisely because of this, many scientists are skeptical about the multiverse, if it can't be verified. It doesn't count as science in the strict sense. But on the other hand, the mathematical derivations of inflation strongly point toward a picture of eternal inflation and bubble relay, the same set of equations that successfully explains the expansion of the early universe. naturally concludes that expansion continues and bubbles keep forming in a much larger space. To match this, the subtle statistical patterns in the cosmic microwave background align perfectly with inflation's predictions. While this doesn't directly prove the existence of other bubbles, it certainly gives us more confidence in saying we might be living inside the very best evidence for the multiverse. At this point, you might still think you're just imagining bubbles in 3 dimensions, but the latest attempts in physics remind us that reality might be even more bizarre. What if inflation is actually happening in a direction we can't perceive? String theory requires space to have 9 dimensions. Besides the 3 we're familiar with, there are 6 incredibly curled up, tiny dimensions hiding right here, right now. They're just so tight that even particles have a hard time probing them. We are quite possibly like an ant crawling on a garden hose. We can only move back and forth along the tube, so we mistakenly believe the world is only one-dimensional. If these extra dimensions really do exist, they might be expanding right along with our 3-dimensional space. In that case, the question what is the universe expanding into gets a different answer. Our 3-dimensional space might just be a membrane, or brine, stretching out into a higher dimensional hyperspace. The accelerated expansion we observe could simply be the warping of this membrane within a larger dimension. Even bolder brine world models suggest that everything except gravity, all particles and forces, are trapped on this brine. We are all trapped within this 3-dimensional membrane. Only gravity can leak out into extra dimensions. That also explains why it appears so incredibly weak. If there are other membranes parallel to ours in higher dimensions, they might be right next to us, just in a direction we cannot see. They might even collide from time to time. Some models simply interpret what we call the Big Bang as a collision event between 2 membranes. The cosmic microwave background might just be the afterglow left by that impact. Following this line of thought, over incredibly long timescales, the membranes might meet again and again. Each time, it's like hitting a reset button, triggering a new cycle of cosmic evolution within our 3-dimensional space. There are even wilder speculations. While our familiar 3-dimensional space appears static, the extra dimensions themselves might be expanding, or perhaps some dimensions are growing larger, while others are shrinking. As a result, the total volume might not necessarily change. Yet our 3-dimensional slice seems to be widening. For now, these are all just hypotheses because we cannot directly touch these extra dimensions. The Large Hadron Collider is currently searching for signs of particles that seem to vanish into hyperspace. But so far, no definitive evidence has been captured. This might mean that extra dimensions do not exist, or it could mean they are even more tightly curled than we imagined. Even so, the mathematics of string theory still suggests that extra dimensions are likely the missing piece of the puzzle needed to describe reality. Taking a step back, even without those hidden directions, the shape of 3-dimensional space itself is enough to rewrite the meaning of where is it expanding to. General relativity allows for 3 geometric forms: flat, like an infinite plane; positive curvature, like the surface of a sphere; and negative curvature, like a saddle. Observations indicate that our universe is either flat, or so close to flat that it is difficult to measure. However, flat does not mean infinite. A sheet of paper is flat, but you can roll it into a cylinder, or glue the edges together to make a donut shape. It remains locally flat, yet globally it can be closed and finite. If space is truly self-contained in some way, so expansion is really just about enlarging the dimensions of this closed structure. It's not moving into some external warehouse. Instead, it's just growing into a larger version of itself. If we follow this line of reasoning regarding closed geometry, it might even leave behind some observable traces. In a donut-shaped universe, light could travel all the way around and return to its starting point. That means we might see copies of the same distant galaxy in different directions. Within the cosmic microwave background, astronomers have tried to look for markers of a closed space on the map of the universe. But they have never found any solid evidence. This could mean one of 2 things. Either the universe is much, much larger than what we can observe, or at least within the scales we can currently detect, this kind of self-contained structure doesn't exist. In other words, the universe might really be like a donut. It's just so huge that light hasn't had enough time to make a full trip around it yet. If we pull our perspective back even further from space, we see that space and time are actually a single, unified 4-dimensional spacetime. The question of its shape thus becomes much more complex. Expansion doesn't just stretch out space. It also alters the relationship between space and time. In the early universe, everything was extremely compressed, and the passage of time was completely different from what it is today. Meanwhile, the concept of simultaneity also loses its unified meaning across vast distances. As space is stretched, time is stretched along with it. This leads to a phenomenon that seems to defy common sense. Some distant galaxies appear to be receding at speeds faster than light. But they aren't actually running through space. It's space itself that is carrying them away, while stretching the very scale of time as it does so. From the perspective of those galaxies, they are virtually stationary. It's just that the rulers and clocks between us and them are changing the whole way. Relativity tells us that, looking from any point in the universe, the picture of expansion looks exactly the same. Every observer feels as though they're at the center, and everything else is moving away. No one has a privileged frame of reference, and there is no true outer edge. More importantly, this stretching isn't just some abstract concept. It's something that can be measured directly. For example, in a nearby galaxy, a supernova might take just 3 weeks to brighten and then fade away. But if that same supernova were to occur in a galaxy, receding much faster and further away, the whole process would look like it's in slow motion from our perspective. The reason is simple. The light carrying the information is stretched during its journey, not just its wavelength. But the time interval between light pulses is also drawn out. So, what we end up seeing is a time-dilated version of events. To put this into perspective with a concrete number, light from galaxies at the edge of the observable universe has a redshift factor of about 10. This means that events over there will appear to us exactly 10 times slower than they would locally. This also explains why the age of the universe is actually a matter of perspective. From where we stand, it's about 13.8 billion years old. But if you were standing on one of those distant, receding galaxies looking back. In other words, the early universe wasn't just more compact in space. Time itself was more compact too. Many evolutionary processes that take billions of years today might have happened on a much faster clock back then. The very first stars, the first galaxies, the first black holes, were all born to that faster rhythm. Going even further, this expansion shatters our intuitive grasp of simultaneity. Two events that you think are happening at the same time might not be synchronized at all for a distant observer. There is no universal now in the cosmos, only individual, local moments. And, as the influence of dark energy grows stronger, this time-stretching effect will continue to intensify. Future observers looking out into the distance will see even more extreme time delays, until those events appear almost frozen in place. This brings us to the script for the universe's future. Based on our current understanding, expansion will make matter and energy increasingly sparse. After an incredibly long time, the universe will head toward heat death. Temperature differences will be smoothed out, and the ability to perform any work will be completely exhausted. The entire world is left with nothing but a uniform void, approaching absolute zero. A rough timeline looks like this. About 100 billion years from now, the very last batch of stars will run out of fuel. There will be no more new stars born. The universe will enter the degenerate era, dominated by cold, dead stellar remnants. Looking even further ahead, about 10 to the power of 34 years from now, protons will likely decay. The fundamental building blocks of atoms and planets will spontaneously fall apart. The universe will consist only of electrons, positrons, and photons floating in an ever-expanding void. Pushing the scale even further, about 10 to the power of 100 years from now, black holes will become the only significant source of energy. They will slowly evaporate through Hawking radiation. Supermassive black holes can even last on the order of 10 to the power of 100 years. When the very last black hole fades away into faint radiation, the universe will have reached its ultimate state. With no temperature differences and no chemical reactions, computation cannot continue. There is nowhere left for life to exist, unless the nature of dark energy undergoes a fundamental change in the future. Its accelerated expansion will keep pushing the world toward this icy end. And in the closer future, the impact is not gentle either, as space-time is stretched apart faster and faster. Distant galaxies will fall out of our observable range. They won't be destroyed, but they will be receding so fast that their light will never reach us. Further still, even the cosmic microwave background radiation will be stretched to wavelengths that cannot be detected. Astronomers in that era will only see our own lonely local group, surrounded by an endless boundless void. The key evidence of the Big Bang will have long since vanished. By comparison, the ultimate endgame of a Big Rip only appears in more extreme hypotheses. If the intensity of dark energy keeps increasing, the acceleration will crush every known force, from gravity and electromagnetism, to the strong force that holds atomic nuclei together. All will collapse. The universe will be disintegrated from the inside out. But regardless of which ending comes to pass, one thing is certain. What we call empty space is not empty at all. The vacuum is a quantum furnace. At the most infinitesimal scales, it seethes with virtual particles, appearing in an instant, then vanishing just as quickly. Too fast for us to ever catch. Yet, they leave behind tangible physical traces everywhere. Just imagine, if you took a microscope with resolution far beyond an atomic nucleus to observe nothingness, as you zoom all the way down to the Planck scale, roughly 10 to the power of negative 35 meters, the once smooth fabric of spacetime would bubble and churn like a pot of boiling soup. Its geometry constantly shifts between birth and death. Virtual particles borrow energy from the vacuum, and the uncertainty principle dictates that the more they borrow, the faster they must pay it back. Electrons and positrons appear in pairs, and vanish in pairs. The entire process might last only 10 to the power of negative 21 seconds. For virtual particles with even greater mass, their lifespan is even shorter. All the various virtual particles allowed by quantum field theory take their turn appearing in this seemingly empty vacuum, and it is precisely this invisible quantum furnace that determines how the expansion of the universe stretches the fabric of spacetime, step by step. These are not mere metaphysics, they are real, leaving fingerprints that we can detect in the lab. The most classic example is the Casimir effect. When two metal plates are placed extremely close together in a vacuum, only virtual particles with wavelengths shorter than the gap can fit between them. The long wavelength ones can't get in. Meanwhile, long wavelength virtual particles still exist outside the plates. This asymmetry between the inside and outside generates a pressure that pushes the metal plates together. This force can be measured directly, which is equivalent to actually feeling the pressure of the quantum vacuum. But what really made quantum foam go mainstream in cosmology is the fact that they should have contributed to the energy density of the vacuum. When physicists calculated it, the result was absurdly large, according to theory. The universe should be growing at a rate far exceeding what we actually observe. To put it in perspective, the theoretical value is 10 to the power of 120 times greater than the actual strength of dark energy. This is one of the most embarrassing misses in the history of theoretical physics. Either our understanding of the quantum world is missing a key piece, or the universe possesses some kind of mechanism that cancels out the vast majority of that vacuum energy. If we could solve this vacuum catastrophe, perhaps we could unveil the true nature of dark energy. Maybe that tiny, uncancelled balance is the very dark energy driving the universe's accelerated expansion. Or perhaps the universe suppresses most of the quantum foam, only letting a tiny bit through. Or maybe our calculation methods are fundamentally wrong from the start. There are even more daring ideas. The vacuum might be filled with hidden fields. Or extra dimensions might be leaking out that vacuum energy. Or the very concept of empty could be an illusion caused by our limited perspective. Loop quantum gravity suggests that space is a network woven from countless discrete, tiny loops. String theory, on the other hand, views it as the result of strings interacting in higher dimensions. Regardless of which side you take, the conclusions are pointing in the same direction. Space is not an empty background, but a structured medium. Expansion might be stretching this medium, rather than creating more space out of nothing. But even if our understanding of the vacuum is still very limited, the future landscape it projects remains breathtaking. What would happen if this acceleration actually keeps getting stronger? There is an extreme scenario called the Big Rip. Approximately 22 billion years from now, dark energy would become strong enough to gradually dismantle all the binding forces in nature. The universe wouldn't just slowly cool down over trillions of years. It would undergo a rapid, catastrophic collapse. A rough countdown would look like this. About 1 billion years before the Big Rip, galaxy clusters would be pulled apart. About 200 million years before the end, galaxies like our own Milky Way would be torn asunder. Stars would be dragged out of their gravitational cradles. 30 minutes from the end, Solar systems would succumb to gravitational collapse. Earth would be flung away from the sun, and the moon would escape from Earth's grip. In the final minutes, molecular bonds would be snapped apart. Gases would dissipate. The reason the oceans would boil wouldn't be due to rising temperatures, but because the distance between molecules would stretch until the forces holding them together fail. At roughly 10 to the power of -12 seconds before the end, atomic nuclei would disintegrate. The strong nuclear force would completely surrender. In the final moment, even concepts like distance and time intervals, those metrics we use to describe our world, might lose all meaning. Of course, all of this depends on whether dark energy will continue to strengthen. If it remains constant, the big rip won't happen. The universe will keep accelerating, but it will slowly head toward heat death. Existing data supports it being basically constant. It's just that the precision isn't high enough yet. Future, more refined supernova observations will continue to investigate whether it's actually changing. If we confirm it is strengthening, we'll be able to calculate the exact countdown. In 1917, Einstein had just finished his general theory of relativity. When he ran into a problem, his equations naturally predicted that the universe was either expanding or contracting. They didn't support a static, unchanging universe at all. But the mainstream view at the time firmly believed the universe was eternally static. In order to accommodate this observational impression, he added a new term to his equations, the cosmological constant, lambda. He interpreted it as a little bit of energy inherent to the vacuum, like a gentle repulsive force, that would just perfectly cancel out gravity to keep the universe standing still. This patch looked quite reasonable and actually worked for a decade or so, until Hubble used the Large Telescope at Mount Wilson to measure the distances and velocities of distant galaxies one by one. He discovered that they were generally moving away, and the farther away they were, the faster they were receding. The universe isn't static, it's expanding, which is exactly what Einstein's original equations predicted before he added the constant. So, he decisively threw the cosmological constant away, even mocking it as the greatest blunder of my life. Ironically, decades later, the 1998 supernova observations invited this cosmological constant back, because we discovered that the expansion isn't constant but accelerating. To drive this acceleration, you need an energy density that uniformly fills space and creates a repulsive gravitational effect. Its effect is exactly the same as the cosmological constant. In other words, if dark energy is indeed the cosmological constant, then Einstein's intuition back then was actually incredibly farsighted. His reasoning may have been wrong, but his direction was right. Looking at it more closely, the value of vacuum energy is incredibly small, but it is not zero. It is about 1 × 10 to the power of -10 joules per cc. This number might seem insignificant, but once you multiply it by the volume of the entire observable universe, it exceeds the total energy of all matter and radiation combined, directly dominating the late-stage evolution of the universe. The problem is, whenever quantum field theory calculates vacuum energy, the result is 10 to the power of 120 times larger than what we observe. This is the famous vacuum catastrophe. Either there is a key piece missing in our understanding of the quantum world, or nature has a mechanism that cancels out almost all of the vacuum energy, leaving behind only a tiny remainder. Some have also suggested that dark energy is not a constant, but a field that changes slowly over time, using this dynamic dark energy to bypass the catastrophe. As far as current astronomical data goes, the simplest cosmological constant model remains the best fit. Now, cutting back to that night Hubble spent observing the sky. At the time, the scientific community was still debating whether spiral nebulae were actually part of the Milky Way. Hubble used Cepheid variable stars as a yardstick to measure the distance to these fuzzy celestial objects, pushing them out to millions of light years or even further, confirming that they were independent galaxies. Then, he plotted the distances of these galaxies against their spectral redshift on a graph. And at a glance, a clear pattern emerged. The farther away a galaxy is, the faster it is receding. This is what we know today as Hubble's law. At first, he thought that galaxies were flying apart through space like debris from an explosion. But that would place the Earth at the center, which clearly violates the Copernican principle. A more accurate explanation is that space itself is expanding. Think of galaxies as tiny dots on the surface of a balloon. Once the balloon is inflated, Every point will see all the other points moving away. Hubble's law thus became the first hard evidence of the universe's expansion. Its proportionality constant is the Hubble constant, which describes how fast the recession speed is for a given unit of distance. Hubble's initial distance calibration had mixed up the types of variable stars. The initial values were on the high side. The calculated age of the universe was only 2 billion years. It was even younger than the Earth itself. Later, the calibration was corrected. The age returned to a reasonable range. Yet, the linear relationship, that the further away something is, the faster it recedes, held true throughout, from nearby galaxies to the furthest visible ones. All of them followed the same curve. This curve not only moved astronomy from an era of two-dimensional star mapping into an era where we could measure the universe in 3 dimensions, but it also brought a key question to the forefront. Will the expansion continue forever? The answer depends on how much stuff is in the universe. Physically speaking, there is a critical density line that determines whether the universe will keep getting bigger forever, or if it will eventually turn back and collapse. Intuitively, expansion pushes everything outward, while gravity pulls everything inward. It's all a tug of war based on the amount of matter per unit of volume. If it exceeds the critical value, gravity will ultimately win. The expansion will slow down, stop, and reverse, leading to a big crunch. If it's below the critical value, expansion will always have the upper hand, and the world will be diluted until it is nearly empty, heading toward a heat death. If it's exactly equal to the critical value, the expansion speed will get closer and closer to zero, but will never quite reach it, just like tossing a ball with the perfect amount of force. It will fly toward infinity, while its speed gradually approaches zero. What makes it even more hair-raising is that this razor's edge density of the universe seems almost like a vacuum. When you break it down, there are only 5 hydrogen atoms per cubic meter. Yet, this very thing determines the ultimate fate of all galaxies, stars, planets, and even us. For decades, measuring the true density of the universe has been considered the holy grail of cosmology. It sounds like a simple task. Just add up the mass of all the matter. Now, just divide that by the volume, and you're set. But things get tricky as soon as we look at the big picture, because most of the stuff in the universe is completely invisible. The rotation curves of galaxies gave the game away a long time ago. Stars on the outer edges are spinning way too fast. To keep them from flying off into the void, we need about 5 times more gravitational mass than what we can actually see in the stars. So, people gave this invisible mass a name, dark matter. It doesn't emit, absorb, or reflect light. It only tugs on the visible world through gravity. We can only identify its presence indirectly, by observing how it affects stars, gas, and entire galaxy clusters. Even when we include dark matter in the tally, the total density of the universe is still only about 30% of the critical density. Based on those numbers, the universe should just keep expanding until it eventually fades into a heat death. But then dark energy arrived on the scene and completely rewrote that conclusion. Dark energy doesn't just bump up the total energy density. More importantly, it carries negative pressure, which, in Einstein's equations, acts as a force pushing space-time to stretch faster and faster. In other words, no matter how much ordinary matter there is, as long as dark energy is in the mix, the expansion is going to keep accelerating. Based on current observations, our universe is composed of approximately 27% dark matter, 68% dark energy, and 5% ordinary matter. When you factor in the negative pressure effect of dark energy, this recipe puts the universe almost exactly at the critical density. It's as if it found a delicate balance between different geometric fates. This brings up the flatness problem. Why is the density so close to that critical value? In most evolutionary models, the density should have strayed from the critical value very quickly, either becoming too high, leading to a collapse, or too low, leading to everything flying apart. To maintain that just right state, the initial conditions would have needed to be precise to countless decimal places. Cosmic inflation offers a way out. During that period of exponential expansion, any initial curvature would have been ironed out. By the time inflation ended, the universe would naturally be very close to the critical density. But then, the coincidence problem pops up. Why do we happen to live in this brief window of time, where matter and dark energy are so evenly matched? Perhaps it's just the observer selection effect. Only in an era where structures have formed but haven't been stretched too thin. Do observers like us have the chance to look up at the sky and ask a question? If we expand our perspective further, the assumption of a single universe might not hold up. In the picture of eternal inflation, the observable universe we see is just a tiny patch within a much larger zone of expansion. Quantum fluctuations can trigger new bubble universes elsewhere at any time. Each one expands, cools down, and grows its own stars and planets. In some bubbles, dark energy is much more intense, causing them to race apart even faster, while other bubbles have denser matter and evolve at a slower pace. Some have even collapsed back in a big crunch, or are currently hurtling toward a big rip. And if you throw quantum mechanics' many worlds theory into the mix, almost every microscopic choice spawns a whole parallel version of history. This means there is no limit to the number of parallel universes. New branches are born every single moment. In some branches, you might end up in a heat death, while in others, you witness the big collapse. And in countless more, you continue to live against the backdrop of an accelerating expansion. Evidence is incredibly hard to find because these universes are causally disconnected from one another. Scientists have tried to look for the fingerprints of bubble collisions within the cosmic microwave background. But so far, there is no definitive conclusion. Even so, the idea of a multiverse has changed the way we talk about expansion. To our corner of space, expansion is an all-encompassing growth. But to a larger structure, it might just be one layer of a much more complex picture. Returning to the question of information and meaning, things get more personal. Every thought in your head, every single memory, is essentially just a specific arrangement of matter and energy. And the expansion of the universe is slowly spreading these arrangements thin. This might look like it's destroying information. Yet physics tells us that information cannot truly be destroyed. The holographic principle offers a new perspective. All the information within a volume can be encoded on the boundary that surrounds it. As the universe grows, the surface area of that boundary grows with it, and the storage capacity increases right along with it. So, there is still room for complexity to unfold. Then, quantum entanglement throws a wrench in the works. It allows particles to remain connected, even across vast, staggering distances. It seems to remind us that information is more about relationships than it is about absolute location. The problem is, causal connections will eventually be severed by accelerating expansion. Regions that could once communicate will end up moving away from each other faster than the speed of light, leaving information locked away inside isolated cosmic bubbles, with no contact between them. On a macroscopic level, the history of the universe still leaves its mark in the large-scale structures and the microwave background. On a microscopic level, local information gets thinned out until it's impossible to recover. Finally, let's push the camera to the ultimate limit of the future. As dark energy continues to stretch space-time further and further, the cosmic microwave background will be redshifted until it's impossible to detect. Distant galaxies will fall off the edge of the horizon one by one. When a new civilization looks up at the sky back then, they might only see a few nearby galaxies with no way to even measure expansion. They will arrive at a conclusion that seems simple but is completely wrong. The universe is static and eternal. If we fast forward about 150 billion years, dark energy will have pushed the vast majority of galaxies beyond the horizon. Their light will be stretched to a wavelength longer than the observable universe itself. The result is that they will disappear from observation entirely. To those living in that era, only our own local group will remain visible. Meanwhile, along with the satellite galaxies, everything will merge into one isolated, giant elliptical galaxy, floating quietly in the vast void. For them, that single cluster of starlight will be the entire universe. At the same time, the cosmic microwave background will also fade away. Because space continues to stretch, the wavelength of this primordial radiation will be stretched longer than the observable universe. Consequently, no instrument will be able to detect it. Thus, all evidence pointing to the fact that the universe had a beginning will be lost. The redshift-distance relationship, which reveals the secrets of expansion, will be impossible to measure. Without being able to see distant galaxies, it will be impossible to discover Hubble's law, and there will be no way to directly prove that space is stretching. So, the universe they see will appear completely static. Based on this perspective, future scientists will likely establish an entirely different cosmology. Concluding that their one massive galaxy has existed from the very beginning in an infinite, static, and unchanging void, they will find it hard to even imagine. That the universe was once filled with billions of galaxies, all moving away from each other as space expanded. In other words, they will live in a universe stripped of its own history. Furthermore, this loss of perspective will only deepen. Future observers will also lose the key clues regarding early evolution. The nuclear reactions that forged the original elements ended billions of years ago. Their traces remain only in the chemical composition of the oldest stars. And they are becoming increasingly difficult to identify. The result is an epistemological crisis, where intelligence and technology remain powerful. Yet the universe offers almost no clues about its own true nature. The methods remain the same, but with so little available evidence, our conclusions are bound to drift off course. This forces us to reflect. Could our current knowledge of the universe also be limited by the era we live in? Have we already missed critical information that only early observers could see? Information now wiped away by the expansion? Perhaps. Civilizations born right after the Big Bang witnessed sights that we can never see again. This same analogy can be extended to the end of time. As space continues to expand, the processes that support life will eventually become unsustainable. Because gas will become too thin. Gravity will no longer be able to pull it together into clouds. Star formation will come to a complete halt. Existing stars will run out of fuel, gradually fading into darkness. Black holes will slowly evaporate through Hawking radiation. Eventually, only thin, sparse fundamental particles will remain in the vast void. The universe will approach a perfect heat death. If there were still observers then, the world they face would be even more deceptive. No stars. No structures. Only sparse particles drifting through an infinitely empty space. They would naturally assume the universe has always been this monotonous, unable to imagine the vibrancy that once existed. Moving from abundance to nothingness. This pushes the question of what is the universe expanding into to the extreme. This question assumes a premise that seems logical but is actually unnecessary. That expansion must have a purpose, an end goal, or some external space to fill up. The reality is more straightforward. Expansion itself is the reason. It provides a dynamic stage that allows brief, complex structures to emerge. Galaxies, planets, and even life itself appear only because this stage is constantly growing. If there were no expansion, the universe would either collapse instantly, or remain in a stagnant, monotonous state forever. But this brings us back to the start. In a universe that creates its own space, generates its own time, and simultaneously acts as its own stage, what is it expanding into even mean? When you ask where is the universe expanding to, you are actually assuming a pre-existing outside, as if a balloon needs air or a city needs the countryside. But the universe is not a balloon, the universe itself is space. As space expands, it's not that it's entering some external place, but rather, as it expands, it creates the very concept of an outside. Therefore, there is no stage independent of the universe, because the meaning of outside is defined by the universe itself. This is not a linguistic trap, nor is it a failure of imagination. It is simply the structure of reality. Before the expansion, inward and outward had no meaning. As it expands, it creates more space, and simultaneously generates the rules that make spatial relationships possible. The universe isn't expanding into somewhere. It completes its expansion by becoming more universe, rather than encroaching upon some so-called non-universe. Following this line of reasoning, our understanding of expansion moves from a mechanical process to a deeper vision. Expansion is like a bootstrap, where reality pulls itself into being, from nothing to something, from simple to complex. Every cubic inch of newborn space opens up new possibilities for matter, energy, structure, and complexity. The universe isn't growing larger for some predetermined end goal. It is moving toward a state that can accommodate infinite potential. We aren't passengers on a spaceship being taken somewhere. We are ourselves a part of this self-creating process. Our consciousness, our questions, and our curiosity are ways for the universe to know itself. The expansion we observe is not separate from us, because we are a part of that expansion. We are complex patterns, self-organized from space, time, matter, and energy, granted the ability to question our own meaning. From this perspective, the superficial paradoxes are resolved, and at the same time, a deeper mystery emerges. If the universe can self-create space and time, and is both the stage and the audience, then existence may be stranger than any science fiction. Perhaps we are living in a process that is self-creating, self-sustaining, without beginning or end. Without inside or outside. The universe is expanding into itself, making infinite room for infinite possibilities, and making space for existences like ours. Looking back on this journey of inquiry, our questions have taken us through inflation and dark energy, the multiverse and quantum foam, the beginning and the end of time. Yet the most precious answer is right before our eyes. The universe is multiplying possibilities, and we are the ones articulating them. So, as we've made our way here, we've realized that what we're facing has never been just some cold, lifeless model of the universe. It is both that vast, expanding void, and the entire stage where we are born, where we think, and where we doubt. Just like that question at the beginning, if the universe truly has rules, is it a product of order, or just a chaotic coincidence? Perhaps we won't get an answer anytime soon, but that doesn't really matter, because the search itself is the very meaning of human existence. And in the span of infinite time, we have only just turned the very first page.